Hello everyone. All right, let's get this review underway here. Okay. So, let's start first with nomenclature. So now we have R and S, right? So now we can, let's first do this molecule, or work on this molecule here. All right. So first, we have, if we count the carbon atoms, we have a pentane. And then we have chiral groups on the 2 and 4 position, right? Yeah. So there's going to be 2, 4. Dichoro, because there's 2 chlorine atoms at the 2 and 4 position. All right, so now we define the stereochemistry. So the way I do it is I use the right-hand rule. I don't know if anyone else does that, so let's look at our stereocenters. We have 2 stereocenters. I'll put asterisks next to them, right here and right here. So let's look at the 2 position. So how I do it is I take my thumbs and I point it in the direction of where the hydrogen is facing. So let's first label our priorities here. So our priority is first the chlorine atom, so that gets priority 1. Hydrogen is priority 4 because it's the lowest priority substituent. And then the third group is going to be the alkyl group over here. And then the second group, not the third group, the second group. The second group is alkyl, and then the third group is methyl. So we could say for stereocenter, at carbon 2, first priority is chloro. Second priority is let's just say the R group. So the rest of the chain, R group. Third priority is the methyl group. And fourth priority is the hydrogen. Okay. So my way of doing it is, you can do the way you were taught, but if you heard of like right-hand rule, like in physics and all that, you can use the right-hand rule here too. So my hydrogen is priority 4, and it's wedged. So that means it's going to come out of the plane of the paper. So if I use my thumb to represent going out of the paper, and then I use my fingers here, it's hard to see, but if anyone has questions about it, they could come see me. But if you use your fingers, you could, and they kind of move in the direction of the priorities. You can assign R and S based on if you used your right hand. If it's your right hand, it's R, and if it's not your right hand, it's S. Okay. So let's see here. We're going from 1 to 2 to 3. So in this case, it'll be so in this case, when you go 1, 2, and 3, you can't cross over 3 to go to 2. It has to go from 1 to 2 to 3, and you can cross over 4. That's fine. So in this case, it looks like it'll be. So if we go from 1, 2, 3, right? It looks like it's S. So it looks S, but remember the hydrogen is on the lowest priority, so it's going to be the opposite. So it's actually R. And if I use my right-hand rule and if we think about it, if I use my right hand rule and I use my left hand, it goes from 1 to 2. It goes from 1 to 3 to 2 if I use my left hand. With my thumb pointing out, it moves from 1 to 3 to 2 in a clockwise direction, right? So that's not going to be it because it doesn't go from 1 to 2 to 3. But if I use my right hand, I see that if I curl my fingers going to the right from counterclockwise, it goes from 1 to 2 to 3, so it's R. So this position is R. So we're going to say, in this case, there's a tie, right? So we'll go over that in a bit. So it looks like at 2, it's R. So we're going to say 2R. Okay, so 2R here. Now let's look at the stereocenter. At C4. Alright, so let's erase some of these numbers here so we're kind of consistent here. Alright. So the 1 position is going to be Coro again, because there's 2 chlorine atoms. Two is the R group again. 3 is methyl. CH3. And 4 is H. Okay. So we got 1, 2, 3, and now 4. Okay. So if we go based on priorities, we see we go from 1 to 2 to 3. So it looks like it's R, right? So it looks like it's R, but remember our rule here, the hydrogen is not on the lowest priority, so it's going to be S. And if we look at our left-hand rule, right-hand rule, if we point out for the hydrogen, it goes from 1 to 3 to 2, so that's no good. But if we use our left hand, you see it points going towards 1, our fingers curl toward 1 to 2 to 3, and I'm using my left hand to do that, so it's S. So we get 2S. So now the question is, since they're both the same substituents, what do we do? So how do we decide which one gets 2R and 2S? Well, since now we're going based on alphabetical, you could think, okay, or sorry, it's not 2S, it's 4S. You can say, okay, maybe if it's 4S, since it's S, and we're just comparing R and S, so maybe the R should come first because it comes first alphabetically. And that's what happens. So we would call this 2R, 4S. So not the other way around, because alphabetically R should be at the 2 position, but you have the same numbering scheme, so that's where our tiebreaker comes in. Dash 2,4 dichloro chloropentane. Okay. So that's how we would name this one. Okay? So you do that same procedure for any stereocenter, and we could, and that's how we would name this compound here. Okay, so you could do this for any structure, a chair, a Fischer projection. It doesn't matter what which one you do. But now we could do one more example. Let's do a Fischer projection. I think I have an example we could go over. Okay. Give me 1 second here. Okay. All right. So the next example, let's do. Let's just say we have this molecule. So let's go over a Fischer projection. So this one's okay. We're going to assign this name here. Okay. Well, we're not going to assign the name. We're just going to predict R and S. But that's, yeah, that might just be easier. So let's get some more practice doing R and S. Don't worry, you don't have to name this one. So let's just find the stereocenters here. We have a stereocenter here and a stereocenter there. Okay. So let's look at the first stereocenter with the OH. So OH is 1. In this case, the alkyl group here is 2. All right, and the methyl group is 3. And hydrogen's 4. So it's kind of, let's see here. What's the best way to do this? You could translate it to the bond line form. But how would that go? Okay. All right, let me see if I can do it. Here's CH3, and then if we flip it on its side, I'm guessing the OH will go in the back. Okay, so it's all about perspective, really. And then the nitrogen will also be on the back side. Like this, maybe? All right. Let's see if we can do this. All right. So for the oxygen, we're going to have 1, 2, 3. So here's 1, 2, 3, and the hydrogen is sticking out to the front of us. So let's just draw that really quickly here. So here's the H, that's 4, right? So it looks like it's S, but since we're going backwards, it has to be R, right? And if we use the right-hand rule, it doesn't work with the R case. Well, actually, it should be R, actually. I think. Let me see. Yeah, as drawn, it looks like it's S. But why would it be S? Let's see here. Yeah, these are really hard to picture. Let's see here. All right. Sorry about that long pause there. Let me just double check something really quick, so I can just confirm something. So it's really tricky to convert these to their Fischers, from Fischer to the bond line. So it's always like a tricky situation. All right. So let me just double check here. All right. Okay, structure, object. Okay, so I was right. Okay. All right, we're good. We're all good, guys. We're all good, everyone. Okay, so it looks like it's R, right? But it's actually S, and that's because the hydrogen is sticking out. So this stereocenter here is going to be S. Okay? And then if we look at, we can confirm this with the left-hand rule, because if we put our hydrogen out front, it's going to be 1, 2, 3, and that's going to be S, going from using our left hand. But you can also do it from the Fischer projection. So remember, in the Fischer projection, the horizontal are wedge bonds, and the vertical are dashed. So if you kind of guess, like, oh, the hydrogen is on the dash, it shouldn't be like that. So we should just switch it. And if we do it from the Fischer projection, 1, 2, 3, it looks like it's R, but since hydrogen is on the wedge, it's going to be S. So you don't have to convert it, but I think it's easier if you convert it, just because if you don't draw these wedge and dash lines, it's going to be hard to see. All right. Now let's do the other one. Okay, here, let's erase this. So now we have the nitrogen. So in this case, nitrogen is 1. The R group is 2. And the methyl group is 3. And then we have a hydrogen just sticking out again. That's H. And that's 4. All right. So if we go from 1 to 2 to 3, we get a, looks like it's S, right? So it looks like it's S, but it's actually going to be R because the hydrogen's on the wedged, sorry. And we use a right-hand rule. It doesn't work with our left hand, but if we use the right-hand rule, our thumb pointing out like the hydrogen, and we move our fingers here. Well, actually, no, it doesn't. It looks like it should be S2. Interesting. Let's see here. Yeah, it should be R though. Huh. Did I draw it wrong? Oh, maybe I drew it wrong. Yeah, maybe I drew it wrong actually. But no, that can't be right. Huh. Yeah, I think I drew it wrong. So yeah, this is more difficult than I thought. Let's see. Yeah, so it might be better just to use the Fischer projection. But there's a way to do this, if we think about it. Let's see. So if we build this molecule, a Fischer is pretty much, yeah. So it's kind of looking on the side here. Ah, I see what I did. So remember, so a Fischer projection, we basically rotate it in a different conformation. So it looks like what I drawn earlier. This. Sorry, like this. Like that. And if we kind of think about, these are pointing like kind of downwards. So it's hard to visualize here. So what I should have drawn is this. So see these methyl groups here? They represent these wedge bonds pointing downward. So I should have drawn it like that. So it's a particular configuration. So what I should have done is this. So let's draw that again. Okay. Now this way is what we should have drawn. Okay? This way. So this is the better way to do it. Okay, so now this is 1, 2, 3, 4. So you see the particular configuration will throw you off. So you don't have to write in configuration. You're going to get the wrong stereocenter. So now if we do this again, it should make more sense. So we go from 1 to 2 to 3. That looks like it's S, but it's actually R because H is on the wedge bond. And if we use our right hand rule here, it goes from 1 to 2. Our finger curls in the 1 to 2 to 3 direction. So that is, actually no, is that still wrong? Yeah, that still looks like. Oh, sorry, no. No, it's R. Yeah. So the thing with the right hand rule is that clockwise and anti-clockwise is no longer apparent. So you just refer to your right hand or your left hand. R is right and S is left hand. So if we use our right hand rule, it actually works now. It's R. And if we go by the method you learned in class, it looks like it's going counterclockwise, right? 1, 2, 3. But the hydrogen is wedged, so it's actually the other way around. So R. Okay? And you can also rotate these things to get into the right right visualization so that the hydrogen's on the dash. And if you do that, you should get the same, come to the same conclusion. So this is going to be, so since hydrogen comes first, we're going to say 2s. So this one will be R. So this will be 2s, 3r, and then you would have, that will be your designation, and then the name. But we don't have to worry about this name because we haven't really gone over naming alcohols and amino groups. So don't worry. This is just for practice for R and S. Okay. So I think that's enough for R and S. Let's move on here now. So let's go to something different. Okay. Okay. All right, let's talk some reactions. So this is on chapters, I believe. We're going to chapters 6 and 7 here. So let's do some reactions. That'll be an important part of this exam is reactions, because you're going to learn a lot of different types. And then when we get to, well, I won't say anything else. Okay. All right. Say we have this molecule here. Okay. So we have a bromocyclopropane, pentane, sorry. Say we have sodium, sodium dilate, or sodium, how do you say this? Yeah, dilate. And then DMF. So this suggests we will have, it looks like SN2, but remember, SN2 we don't get, we can't do on tertiary. So this hydrogen right here is a tertiary carbon. So you always look at the position. So look at carbon with leaving group. So leaving group, you're going to always look at when it's a halogen or OX, where that's a good leaving group. X has to be like a halogen or one of those sulfur leaving groups, you know, like O, MS, OTS, and then OTF, those groups. So you should know what those structures look like. And when we encounter it, I'll draw it for you. Okay, so in this case, we're going to predict an SN1 type reaction / E1. And that's because we have a tertiary position. So tertiary always points to SN1, right? So we're going to draw a bunch of structures here. So this stereocenter stays the same. You don't change it because you didn't react at it. So now I'm going to draw a generic bond here. So this will now be our substitution. This will be SH. Okay. So this kind of bond, when you don't make it look like a fully dashed bond, this means racemic or mixed stereochemistry. So this could either be mixed stereo. Okay. So if you draw that, you're all good. That's fine. But now we also have to draw all the E1 products. So there's a lot of E1 products. So let's draw them all. So E1 is when we get the alkene. So we get this product. That one. Okay, yeah, so they're not, it's not actually symmetrical, so you get a lot here. This one. See, now the double bonds are not symmetrical because one of them is separated by a CH2, whereas this alkene on the left is not. Okay, so you get that product, and then you can get the exocyclic alkene, which is also a possibility here. So we also get the alkene that's coming out of the ring. That's called exocyclic. So if we asked for an SN1 mechanism, we might ask you to draw just the major substitution product, but just to be safe, you should also draw the alkene product because E1 is all often accompanied by SN1 because, remember, SN1, the base strength doesn't matter. What matters is the formation of the carbocation, so that's why we get these two products. All right? So these all happen through the carbocation rearrangement. So it happens through this. So now this is planar plus. Okay? So if SH comes in here, so the nucleophile here is SH minus. So this is sodium plus, SH minus. When we dissolve it in solution, it's going to separate into ions. Sodium does not do anything, so don't attach the sodium. So this could do this, or if it attacks this hydrogen, SH minus can do this, an E1 type elimination here. So that will give us this product. Now, if it went here, that means SH minus attack this hydrogen here to go over there. And then to get this product, it meant, let's just erase this for now. It meant this hydrogen was attacked like this. So you get a variety of products there, okay? Maybe I should color code it. So this one, let's make this green. So this one will be attacked from here. Okay, so say that's green, all right? And then this one, let's go with blue. Oh crap, nope. Stop. So this one is when we attack it from this position. Oh, that's not going to work. No, I don't want that. Okay, never mind. Go back. Here you go. All right. So that would be the formation of that product. And then, yeah, it's not going to work. Anyway, we can just draw over it. And then lastly, let's do this first alkene product as I don't know, purple. And this will be when this happens. Okay, that's not going to work actually. Does this work? No. Does this work? There we go. Perfect. All right, never mind. Purple. Oops, wrong pen color. Okay, and then right, and then if SH, here's SH again. If it attacks the carbocation directly, so I'm pointing at the carbocation, it goes to the substitution product. So a lot of different mechanisms that can occur here, and that's why the product distribution is so messy. All right, now let's go over a different example here. So I went over this in office hours, but let's just go over it again for students who couldn't make it to office hours. All right. So, we have cyclohexane. I could just make it a little bit different. Okay. Oops. All of these conditions. So we look at this carbon. This is a secondary carbon. And we have a secondary carbon, but with a good leaving group. But we have a poor nucleophile. Water. So these conditions are favorable again for SN1 and E1. Alright, so we should get substitution here, and we're going to draw our product as racemic because it's SN1, so we're going to draw water here. Okay, so you can, if you just leave the bond as normal, that means it's racemic. So this means racemic too. All right, and then we get two different kinds of E1 products. Oh, let's see here. No. Let's see. Do we get two different E1s? Well, this one's a little more, I would say, a little better to draw. Okay, let's see here. So then you get the E1 product, right? All right, so we're going to get, let's just draw it right here. We're going to get this one, and then this one, like this. So these will probably be the most stable products. So you can get an alkene in that position or the other position. So yeah, so these will probably be the products we get. But let me just draw this a little bit better. Okay, so these will be the major E1 products. You could also get, I don't know if you talked about cis and trans isomers for alkenes, but you can also get that as well. But it's probably enough. If you just draw these, you're good. Okay, so that's SN1 too, even though, so this looks purely like an SN1 conditions, but yeah, that's what we get. Okay. Let's go over now a different example. All right, so this example, so we have CH3, 3COK. So the thing on the bottom usually is solvent, so I wouldn't worry about that in terms of what to write. That's just a solvent, so this is a solvent. Of course, we will not write solvent on the exam, so you have to predict this on your own. And this is the nucleophile. Okay, so the potassium there is just a counter ion, so it's plus on the potassium, negative on the oxygen. So in this case, we have a primary carbon. Our leaving group is a good leaving group, so it's mesylate, which is this group here. So these are good leaving groups because this group right here I've just drawn is the conjugate base of a strong acid. So conjugate base of, in this case, a superacid. So so very good leaving group. Very good leaving group. Okay, so our primary carbon, a great leaving group, but we also have the nucleophile. So the nucleophile looks like this if we were to draw it out. Okay, so it's a strong base and bulky. All right, so strong base and bulky because of the tert-butyl group. So tert-butyl. So when we have these kind of cases, it's we're going to see E2 because of the strong base. Even though it's primary, our base is very bulky, so it's going to be an E2 type reaction. So we're going to get E2-like conditions. And remember E2, oops. Remember when we have E2? There's no way to form different alkenes because it's a primary position, so the base can only do one thing, which is abstract this proton here, go here, kick off the leaving group. And what we get is this bond, this primary, this product. So this is butene. Okay, so that's the only product we can get in this reaction. E2, only one product because it's primary. And then, yeah, that's the only product we can get in this case. All right, let's move on here. All right, now we have OTF. All right, so what's the major product of this group? So this is, remember, polar aprotic solvent. So this is DMSO. If no one knows what DMSO is, it's like this. And fun fact, if you ingest DMSO, which you shouldn't, it's dangerous. That's why you wear gloves. It feels, you can actually taste, according to my buddy, you can actually taste, you can actually feel the taste of garlic. So that's something intracellularly that triggers a response. So the MSO, really weird stuff. But it's very soluble in water, so you can, we can probably easily, I don't know, flush it out. But when handling this chemical, you ever spill anything on your hands, it absorbs through the gloves and can potentially absorb on your skin, so you want to change your gloves right away. But when you get the when you get in the lab, I don't think you'll be working with DMSO at all, just because some of the safety precautions. So that's polar aprotic solvent. So when we have this, it usually screams SN2, right? But let's take a look. So our carbon here with the leaving group is a secondary carbon atom. Good leaving group. So this is called triflate. So triflate looks like this. So it's trifluoromethane. This group, trifluoromethane, sulfonate, which is SO3 attached to an R group, like this. So this is a very good leaving group too, because it's a conjugate base of a superacid. So it's very good. And then our nucleophile, it's sodium plus, and this is an azide. So the azide comes from, so the azide right here, A3 minus. So that's a source of azide. This group here, and it's a relatively weak base, but good nucleophile. Okay. So in this case, whenever you have N3, it's going to do SN2. So this is going to be SN2. All right, so we write our reaction here. Remember, in SN2, what happens to the stereocenter? We are going to invert it. So now this is going to leave, and we're going to get, well, we shouldn't write like that, but. So make sure you write it very clearly. Well, that's all right, I guess. It's okay. N3. Okay. Okay. So to kind of differentiate between the SN1, we can actually write this a little bit differently. So let's do like a solid line within within, so like kind of like a little shaded part here, and then also wedge here to indicate that there's mixed stereo. You could do that, or you could draw both of them if you want, or you can draw one and say racemic, because there's only one stereocenter. Well, actually, no, we can't say racemic. It's better to say plus other. Well, it might be best to do this: draw a dashed and wedged together to indicate it's mixed. Okay. So that's SN2. So whenever you have a product apolar solvent, you can think SN2, but sometimes, like in this first example, we put a polar apolar solvent there, but the carbon is tertiary, so we don't see SN2 reactivity. So just be aware of that. So DMF is also a apolar product solvent. A polar aprotic solvent, and it looks like this. Okay, so see, in these type of solvents, none of the atoms are nucleophilic enough to outcompete the other nucleophile, so that's why they don't react. But sometimes they can react in certain reactions, so we always have to be wary of the functional the structures here. And I did post something about the structures of these solvents, so you can always look that up. All right, so let's do one more reaction, and then we'll move on here. And we don't need to do that. Okay. All right. All right, we have CH3ONA. So methanol is the solvent you would use in this case, so we're just going to label it solvent. Sodium is plus charge, and the oxygen is negative charge, so our nucleophile is O minus CH3. All right, let's look at our substrate. We have a secondary carbon atom. And we have a good leaving group. So we should expect, in this case, nucleophilic here is basic, strongly basic. But also good nucleophile. Good nucleophile, but strongly basic, right? And then remember, if we have a secondary position, that will always favor most predominantly E2. Okay? So in this case, it's basic. It's a strong base, secondary carbon atom, good leaving group. So in this case, it's going to favor E2 conditions. And that's because it's a strong base. Now, you can get some substitution, but I doubt that's be the major product. So it's going to actually be E2. So E2, we have two different possibilities, right? We have this hydrogen here, because one of them, remember E2, in order for E2 to occur, one of these hydrogens has to be wedged, sorry, because it's kind of like a backside attack with SN2. In this case, they have to be anti-parallel or anti to each other to effect the E2 reaction. Like that, okay? So one product is boom, 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 boom. This product, and get another product. Now, if we do the other product, this one, the other product forms by rotating this bond. So the other product, we can get the other product. Okay. So say we have this structure here. The methyl groups can rotate, right? So the methyl group, since we have it right here right now and the hydrogen in the back, we need the hydrogen to be wedged to do E2. So, but this can rotate, right? And now, one of the methyls will be here. So one of the methyls will be on the line. Then the hydrogen now will be wedged, and then the other methyl will be dashed. Yeah. So kind of think it's like rotating 120 degrees in one direction. So now we have the appropriate conformation to do the reaction. So let's just write these CH3s out so it's easier to see. And now the base will take this hydrogen here and come here and kick off the chlorine. So in this case, the product we get is now we lose all stereochemistry because the double bond has formed. So we're going to draw it like this. And then you can get two different products here, and usually you get well, you only could get one product actually. So it's that. Like that. Okay? So those are the two different products we can get. Alright, so that's about it for reactions. Like that. Okay, so this will be E2. Another example of E2, and the major well, don't worry about major product because we're not talking about that yet, but it's usually the more substituted alkene. All right, let's move on now to, let's do some vocab. Okay. Let's do some vocab here. All right. Let's just do bullet points. All right. So good nucleophiles tend to be all right, let's put in a blank here. Be blank. Well, I kind of just said it, but blank, negatively charged, and have blank orbitals. Okay. So if we were to, give a multiple choice, let's just say, okay, good nucleophiles, do they tend to be more or less electronegative? Well, remember, nucleophiles, they want to donate. So they have to donate electrons, right? So it's best if they're less electronegative, because if they're too electronegative, they don't want to form a bond, right? It's not favorable if they're already pretty happy on the atom that they reside on. So usually that's why we see nitrogen's more nucleophilic than oxygen, and carbon's the best nucleophile if we can have a negative charge on carbon. Okay, so less electronegative. Now remember, probably in class in your textbook, we showed experiments where you have a more negative charge on the nucleophile, the faster the rate, so it's going to be more negatively charged. Say, for example, OH minus versus H2O. OH minus would win and have, in this case, what kind of orbitals, smaller or larger? If we compared, the reaction of this group here, well, let's do something else. Let's do like OMS, and then do the same thing, OMS versus iodide minus and versus chloride minus. We'll see that, well, it depends on the solvent, but if we just keep everything equal, like DMF or acetone, this one will have a greater rate. So the K1 here will be much greater than, so see, this is K1 and K2. K1 will be much greater than K2. Okay, and that's because iodide has a larger orbital, and so it's easier to form a bond when it comes and approach for substitution. So have larger orbitals, so larger valence orbitals in this case. So yeah, we want to have larger orbitals in this case. Okay, let's move on here. All right, some more vocab. A levo rotatory mixture. Oops, I spelled it wrong. Rotatory rotates plain polarized light So this would rotate it to the left. Remember, dextero is, right-handed, and then left to the left is going to be levo rotary. Okay, to the left, and we give it is given a negative. So we're going to say negative / negative sign. Okay, and what can we say about its absolute stereochemistry? And has an, or what can we say? Is it R and S? It has an undetermined. We could say undetermined stereocenter, right? So we can't actually assign R and S. So we can't assign R and S to levorotatory and dextrorotatory. So we can't assign R and S to plus or minus based on if it's a plus isomer or a minus isomer. We actually have to go in and assign it ourselves based on the crystal structure. So we can't do that. All right, so we can't assign it arbitrarily like that. All right. Okay, boom, boom, boom. So let's see what else we should go over here. All right. All right. So in an SN1 reaction, okay, the leaving group all right, so let me just pause the video here and I'll resume in a bit. I need to go get a drink of water. Okay, so in an SN1 reaction, the leaving group, what can we say about the leaving group? All right, the leaving group leaves blank as the nucleophile enters. Okay, which creates a blank intermediate. Okay. All right, so the leaving group leaves, is it before, after, or at the same time as the nucleophile enters? But we know for SN1, the first thing that happens is the leaving group will depart and form an intermediate. So it leaves before the nucleophile gets a chance to enter and create a bond. And this creates a carbocation. We could say it's carbocation, or we could say planar. A planar intermediate, right? And then, in addition, this is blank accompanied by an elimination reaction. So for SN1, it's always accompanied. So there's no way to get a pure SN1 substitution, and that's because the electrophile, or the carbocation, is so reactive that any pathway that quenches it or reacts with it will happen. So it's not possible to favor one pathway completely over another, but you can push it to one direction almost exclusively, but you'll always get some product mixture. Okay? So SN1 leaves with 4, the nucleophile enters, and this will create a reactive intermediate. All right. All right. So if we have 2 stereocenters, two stereocenters that that are not exact mirror images and are not superimposable and are not superimposable, right? We call them diastereomers. Okay? So, they blank. They have, so what do they have? They have blank, similar, they have blank properties. So what kind of properties do they have? So remember diastereomers. If we think about cis and trans diastereomers or stereoisomers, like alkenes, they have different properties, right? So in this case, they won't have identical properties. They won't have the same properties, except in chiral scenarios. Those are enantiomers. They'll have totally different properties. Okay, so they're always different. And that's why we can separate them based on their properties. That's how we kind of can separate stereoisomers, if we can make a diastereomer of the 2 different diastereomers. All right, let's move on here. All right, so let's talk about leaving groupability. So increasing the strength the conjugate acid blank the leaving groups ability to leave. So remember, leaving groupability is based on the strength of the acid. Because remember, as the acid increases, acid strength, the conjugate base decreases. So, and when the conjugate, so let's just say, conjugate base decreases, and that means it's more stable as a base because it doesn't want to react. So the acid strength increases, we get a conjugate base that is much weaker. The conjugate base strength decreases. Maybe we should say base strength decreases, and when we do that, it's more stable as a base by itself. That's why, you know, HCl, nitric acid, you never see the chloride or nitrate act as bases, and we say the acid-base reaction only goes in one direction to completion, and that's because they're way too weak as bases to actually compete in an equilibrium reaction. So that's why we use strong bases, strong acids, so we can go in one direction and devise a synthesis based on those properties. All right? So increasing the strength of the conjugate acid would increase. Okay? Would increase or increases the leaving groups. Let's use some proper English here. All right. Okie doke. All right, let's talk about IR now, just because you can expect IR on the second exam. An alkyne triple bond. Okay. So I would recommend memorizing these wave numbers by doing problems. Okay, but we might ask some questions about them. So an alkyne triple bond. And the IR spectrum has a peak at about. So we would give you, this is like a multiple choice type of question. So you have options to pick from. So about what wave numbers? So inverse centimeters, remember, is wave numbers. So remember alkyne and nitrile C triple bond N, they come around about 2200. So don't have to be exact here, but just in the ballpark range, 2200. And that's because, remember, triple bonds, they're stronger bonds, so they should appear at higher wave numbers than, say, a double bond. And then the only exception is when you have two small atoms like C and H. Bonds to smaller atoms, they're really hard to vibrate, so that's why they occur at like 3000. Okay? All right? So that's for an alkyne, okay? An alcohol, OH, IR. So this one is very, very distinct. Has a peak at around. Or we could just say about, in this case, just to keep it consistent. Again, you'll be given a list of options here, and you'll have to specify. So we don't strictly ask you to memorize it. We just ask you to predict, is it this one, or is it this direction, or this direction, etc. So 3300. But when assigning the IR spectrum, so you will have to be able to identify the peaks. Okay, centimeters, and this peak, we have to, what kind of shape is it? Which is generally speaking, is it broad, narrow, or doubled? Does it have two peaks? And in this case, OH usually has a broad peak. And that's because it's broad because there's hydrogen bonding. So you kind of think about, here's a generic OH bond, bonded to another OH bond, bonded to another OH bond. So that's why that stretching frequency is so broad, is because there's a lot of hydrogen bonding interactions going on there. Okay. All right. So don't worry anything about chapter 8. We don't have to think about that yet until the final But let's talk about some more substitution reactions. So a primary haloalkane in the presence of a weakly basic nucleophile is likely to undergo is it SN1 and E1? So is it SN1 and E1? SN2 or E2 or no reaction? So which one will it be? So we have primary haloalkane that favors SN2, right, or E2. So we can cross out SN1 and E1. So that's not going to happen. Now, is it SN2 or E2? And we know the reaction is going to happen, right, because SN2 favors reaction with a weakly basic nucleophile. So in this case, so assume the nucleophile is good. Weakly basic nucleophile meaning, okay, it's a nucleophile that's a weak base, so it'll favor substitution, right? So it's not going to be E2 because that's strong base. And in this case, we're assuming the reaction happens because we have a primary haloalkane. So we could cross out no reaction, so our answer is SN2. All right. And then lastly, talking about the mechanism for the E2 reaction. Remember the E2 reaction, the leaving group. The leaving group and acidic hydrogen H in an E2 reaction must be blank in the transition state. So remember when I drew those hydrogens, they were always a wedge and dash bond involved in the transition state. So in this case, the bonds must be anti-periplanar. Or you could say anti, but we prefer anti-periplanar. And that has to do with how the orbitals interact, but we're not going to go much into that. If students are interested and need a better explanation, come see me. All right, there we go. So we went over vocab, a lot of vocab. So that's kind of a summary of what you should know and be expected as part of the exam, okay? All right, so we went over RS, but maybe let's now do some examples where we think about some of these molecules. Are they R, S, or achiral? So is it R, S, or achiral? All right, just a few more examples here. Boom, boom, boom. All right. So if you did all the examples in the practice exam, and then in the discussion worksheets, you should be good. In good shape. Okay, so let's do this one first. All right, so let's assign our priorities here. So our priority is, so we have C, then H, and then we have Br, and then we have C, O, OH, and then on the alkene, we treat this as C-C-C, okay? Wait, maybe I should move that. Oh, shoot, too far. All right. So in this case, for an alkene, we think of it as C bonded to 2 carbon atoms. So C-C. Like that. And then this group is going to be CH2 bonded to CH3. Okay? So if we think about it, C bonded to the O is probably going to win. So we're going to call this position number 1. Okay, number 2 would be, we have CCC, so this one is going to be number 2, even though there's a bromine on the other one, and that's because it's attached to a hydrogen first, 2 hydrogens, so that's the point breaker. CC versus CH2 would actually win the tiebreaker. And then this one will be the third one because CH2 beats, bromine beats out the CH3 that would come next. Okay. So the lowest priority substituent is not on the dashed. So when we assign it, it looks like 1, 2, 3. So that looks like R, right? Wait, maybe it should be R. Shouldn't it be R? Maybe I got this wrong. Let me see. Ah, okay. Okay. So in this case, we probably have to reconsider these numbers. So let's reconsider them. Okay. So this is CC and then H. But this one is CH2 and then Br. So since it's attached to Br is greater than chlorine, so we're going to attach this one as number 2. Oh, sorry, Br is greater than carbon, so this one's number 2. And then the alkene is 3. My apologies there. Okay, so we get lowest priority substituents not on the dashed, so it's going to look like it's S, right? So it looks like it's S, but it's actually R. So this one will be R. And I think if we were to rearrange it here, it would actually look, well, there's no need to rearrange it though. But if you were to rearrange it, I believe you would see it at, let's see. If we did rearrange it, say we did this. Okay, we're going to rotate things a bit. So now the dash is the ethyl group. And then what comes over here is COOH. And then on the wedge is going to be the H2Br. All right, and we do the same thing here. 2, 3. Yeah, so now it looks like R, right? So yeah, so we rearrange it now that the priorities are in the right positions. It does look like R as well, okay? And then if we do it, yeah, so it looks like it's R, right? No, now it looks like it's S. So should it be S? No, I think it should be R though, but I think I rotated everything correctly. Huh. All right, when in doubt, everyone. Let's just check it. Okay. Sorry. I thought I knew it, but maybe I'm rusty. What the heck is going on here? Alrighty, let's see here. Then we have another group here, so it's going to be wedged and dashed. So we get CCOH, and then this one is CH2Br. Oh, so I'm right. It is S. No, it's R. So I'm wrong. Okay, let's see here. All right. So as drawn, we got it correct. So maybe they both have to be on the lowest priority. They both have to be matched. So it's right now, it looks like it's S. Right? Or did I rotate it wrong? Let me see. No, I don't think I did. Huh. Okay. Well, yeah, that one's hard to do. Yeah, so maybe we have to rotate them in the... I'm very curious why this... Okay. Interesting. Alright, so maybe the best thing to do is just figure it out and just assign it. Yeah, this example perplexes me quite a bit. I don't know why it wouldn't work this way. It should actually. Yeah, I'm not sure. Yeah, but it should be R. So maybe I don't have enough. Not getting enough sleep. Yeah, I don't know how to explain this really. I'm pretty sure I rotated everything correctly. Okay. So maybe we don't rotate that one. Let's rotate something else. Okay. So, so let's rotate it this way. Okay, and that will put the wedge on the CH2 here. So 1, 2, 3, 4. Well, no, now that's still S, isn't it? 1, 2, 3. It still looks like it's S. Huh. So maybe we're rotating things a little bit weirdly here. Wow, that's a curious thing we got going on here. Yeah, I'm not sure why. So even if we rotate it, it doesn't seem to do anything. Because now the lowest priority substituent is in the back. But it looks like it's S still. Why is that? Okay. So let's not waste any more time on this. Yeah, I'm not sure why it's not. Yeah, I don't know why it's not. It's looking so oddly here because it looks like it's S. Did I get the substituent wrong? I don't think I did. Right? Yeah, I'm not sure. Okay. Yeah, I don't think I got the substituents wrong, but if I did, huh? Yeah, that's 1, 2, 3. Huh. Interesting. Okay. So yeah, I guess don't switch it like this. I don't know why it won't work. And I think it's because you don't need to get both of them on the you don't have to get both of them onto the proper substituents here. So as long as you as long as one of them is either the highest priority is on the wedged or the lowest priority is on the dashed, as long as one of those are good, you should be able to sign it right away. But I don't understand why this one isn't matching up. I think maybe I'm rotating it incorrectly. So yeah, sorry I couldn't figure that out. Okay. So yeah. So if the highest priority substituent is already assigned, just go based on that, and it should be. But even if we do it that way, it still doesn't make sense because the hydrogen is not on the lowest priority substituent. So I guess you have to do it according to R. So it'll be R in this case. All right. Yeah, this one's a really weird example. And I don't know why that is. Let's see. Because, yeah, if we were to rotate it, yeah, I'm not sure. It should be like that. And then you get OC like that, right? So, it should rotate quite easily here. But is it possible that we don't have these priorities right? Because right now it looks like S. Huh, what a weird example. I'm pretty sure I'm rotating everything right though. I mean, right? Huh. Because now it looks like yeah, it looks like S. Okay. Well, I'm guessing the reason we see this is because Honestly, this doesn't make sense, actually, to be honest. Because I'm just rotating it all three substituents, so I should get the same stereocenter. But if I switch priorities, it'll be S, so that can't be right. But why am I getting these substituents mixed up? This should work. Oh. Sorry everyone, maybe reach this part of the video just so I skip over it like 10 minutes, because it's gonna just be me troubleshooting this weird problem. Yeah. Yeah, I don't know why. Okay, maybe you shouldn't have to do this, but let's redraw it. So let's draw it like this. Boom, boom. So they drew it to kind of kid with you a bit. Boom, 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 boom. CH2, BR. And then here is my COOH. Okay. Alright, so maybe the orientation is just weird. I don't know why that would be, to be honest. Okay. 1, 2, then 3, 4. So it looks like it's S, right? But now we know it's R. So let's rotate it a bit. Well, not easy to rotate. But if we did, I think we would get like this. One, two. No, it still looks like S to me. Yeah, does it still look like S? It still looks like S to me. Why is that? Yeah, so I'm not crazy. It still looks S to me. But if we switch those two, it'll be... It'll still be R. It'll go this way now. It's R. Yeah, so it still looks S. So now it looks like we switched to Stereocenter. Well, alright guys, let's just move on, because yeah, I do not know why. It's just gonna bug me all day. I'll probably think about it later when I'm not doing this video. Okay, let's do the next one. Sorry, that took forever. Jesus. Okay, let's see if we got this right now. So now it's a hydrogen here that is on the dashed. Sorry, the wedge. So now let's name our priorities. So our first priority is probably going to be this oxygen here. So that's 1. And then when it's substituted here, that's always going to be highest. Then it's simple alkyl chain. And then this one will be our third one. And hydrogen is 4 as always. So if we look at our priorities, it looks like it's going this direction. So that looks S, right? Wait, isn't it S? No, sorry, that's R. Oops. So that looks R, right? So, since the hydrogen is on the wedge when it should be on the dash, we're going to say it's S. And if we use the right-hand rule here, it is going to be S. 1, 2, 3. Yeah, so it's S. Good. All right, that one's a lot simpler. Yeah, okay. Just give me 1 second here. Oh, wait a second. Wait a second. I think I know what's going on here. So, the lowest priority substituent has to be either wedged or dashed. So let's revert this one again. So let's see if I can figure this out. Sorry guys, this is important though. So let's say this is our carboxylic acid group. Y'all don't know what that is, don't worry. Okay, so I think the substituent is still this. 1, 2, 3. And this is 4. So that will be R. Okay, so that's R. Now, if I do... Yeah, so now if I put my thumb in the direction of the substituent, it goes 1, 2, 3. So it's R. So I think I'm right in this case. So, I have to double check, but yeah, remember when you have C, the point of first difference is the carbon versus the hydrogen. So you don't compare to bromine yet because that comes after the hydrogen. So I believe the alkyl chain here would be R. Okay, so it has to be. The lowest priority substituent has to be either dashed or wedged. So that's our comparison, really. Okay? So that's how we rotate it, and then we get R in that case. Okay. So I think that's what it is. Okay, everyone? So this is... So we're good, but we have to make sure that everything is... the dash is at least on the wedge or dash bond. And I think it checks out here as well. All right. So when we have CHCC, and then we're comparing CHHBr. So even though there's CBr, we have 2 hydrogens here, and the point of first difference is when one of these hydrogens is a carbon, so that would automatically win out because carbon is higher than hydrogen, even though there's a bromine there. I think you've learned that when you have more substituted carbon atoms, they always win out. Over CH2, and that's because the point of first difference is the hydrogen, and when you compare the hydrogens, it should be carbon that wins out on this case. Okay, so that's a tricky one. Yeah, that's a very tricky one. So I think we solved it there. But so yeah, don't use this analogy here. We're going to switch it to this one. You should rotate it first. But honestly, if you did that one, you still get the right answer, but it might not work for all the examples, so I wouldn't do that. Okay, let's do a few more here. BR. Okay, so look at this example, right? We have CH2, CH2, Br, CH2, CH2, Br. So these two groups are the same here. These two groups are the same R group, achiral. So remember, anything that doesn't have a stereocenter is achiral, so it won't produce a set of enantiomers. All right, let's do this last example here. So we have, all right, an alcohol and a cyano group in the same compound here. Let's see if we can get this. Oops. Oh, we have some fancy paintbrushes. Okay. So CN. All right. So our stereocenter. So this OH is not given a stereocenter, so you don't have to assign it. It's the one that it's this one. All right. So hydrogen is 4. Cyano. Okay. So we have CH2. And then COH. Then we have CCCC. So this is CCCC. All right. The CN is C. We treat it as a triple bond, so 3 N's here. And then H is 4. And then this last group is C, H, H. Then we have CH, CH3, OH. Okay? So the point of first difference. So this carbon at the top here is bonded to 3 carbon atoms. So that's going to outcompete the CHH. So this one should be is between this one and this one. This one has 3 nitrogens, so that one's going to be carbon. So nitrogen is greater than carbon. So this is number 1. CCC is greater than 2 H's and then another C. So this is going to be number 2. And this last one is number 3. Okay, so the point of first difference. So it's kind of this, very organized system of listing priorities. So we're always given the right enantiomer. So that's just a nice way of determining, like, do we have this enantiomer or the other one? Okay, so if we do it that way, we're going to say, okay, 1, 2, 3. So if we use our rule here, it looks S, so it looks like it's S, right? So it's going counterclockwise, so it looks like it's S, but the hydrogen is not in the right configuration, so we must do the opposite, so it's R. And if we use the right-hand rule, our curve, when we assign priorities, it looks like it's going in a clockwise direction, so it's with my right hand, so that's R. So this last one is R. This one's achiral. This one is S, and this one's R. All right, sorry about that long detail there. Looks like I was rusty on the rules myself. Okay. Boom, 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 boom. Okay. So, whoops, my cursor's here. Don't want that. All right. So let's look at these rings here. So we have okay. Say we have a some boom 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 boom. So let's say we have some rings here. Okay. Let's just say we have a bunch of cyclohexanes, okay? All right. Alrighty. So we may ask some questions about, optical activity. So that's definitely something we may consider. Alright. Bam, 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 bam. Alright. Alright, 1, 2. Alright, there's a lot here. That's good. So we get more practice. We'll keep working hard here, and so we can enjoy the break afterwards, right? Oops, wrong one. Alright, that was a lot. Alright, so we have, bam. Alright. Alright. So for these rings, I want you to answer which of the above. Which of the above cyclohexanes are optically active? Looks like my sorry, my handwriting is really bad. That's why I'm not an artist. Alright. So optically active means they have at least one chiral center and that has no mirror plane. Alright. So this one, so let's just call this number 1. It has a mirror plane, right? Well, yeah, it has a mirror plane, but it's not chiral, right? Because these two sides are equivalent. So these are equivalent substituents / sides of ring. So not chiral. So let's cross out this one, right? Okay. All right, but this number 1, number 2 here, we see that there's a chiral center here and a chiral center here, and they're not related by mirror plane, so not meso, so this one checks out. So that one should be chiral. All right, number 3 here. So just like number 1, there's two sides of the same ring on the top stereos. This thinks is a stereocenter, right? But it's not. And then the other position with 4 different substituents, there is none, so this one does not check out either. All right, how about letter 4 on number 4 here? Okay, it checks out, right? This is a stereocenter, all 4 different substituents, and this is also a stereocenter, all different substituents. So this is a chiral compound, so that will be optically active. All right, letter E. Sorry, did I say E? I meant 5. Number 5. So here we have a stereocenter, and then here we also have a stereocenter, right? 4 different substituents, so E5 checks out. All right, number 6. Just like the cases we've seen before, it's 1,4 substituted. So 1,4 disubstituted with different substituents, they'll never be chiral because 2 sides of the ring will be exactly the same. So this doesn't check out. And likewise for G, it's symmetrical and it has the same 2 substituents around the ring. So this one will not pan out either for number 7. And then for 8 here, all right. So we have potentially 3 stereocenters, right? 1, 2, 3. So we look at the 2 ethyl groups at the top left here. They don't have the same size as substituents. this one has a CH2, then the other alpha group, and then one has the alpha group, then a CH2, then another alpha group. So this one checkouts as well. So it's going to be numbers 2, 4, 5, and 8. Okay, so something like that. So be able to do that. All right. Now let's wrap up our review here, because this review is almost getting 2 hours long. So we're going to wrap up with some this or that molecule or this off. You're going to choose some more multiple choice, and then let's go over stereoisomers, the relationships, and then we'll do one mechanism, do IR. So this might be fairly long, but if you watch it, I think you can be more confident when taking the exam. Okay. So let's see here. All right, so we're going to say what would give a faster SN2 reaction. Okay, so I'm going to give you a list of options. So we're going to decide which one would give a faster SN2 reaction. Okay. All right, so we have a primary bromo versus a tertiary bromo. Okay, so remember SN2, we like primary, so we're going to say this bromo. All right, so often we have protic solvent versus aprotic. So remember, protic solvent, for SN2 reactions, you need a polar solvent, but if it's protic, it might tie in, or it might sequester your nucleophile. So remember, in SN2, the rate is also dependent on the nucleophile, whereas in SN1, that's not the case. So in this case, we would want a aprotic solvent because it would give us a better SN2 reaction, because it won't surround the nucleophile and inhibit reactivity. All right. So as the nucleophile H2O. Okay. All right. Is it H2O versus H2S? So remember, the less basic you are and the larger the orbitals are, the more nucleophilic you are, and that's because you can donate electrons better and you can have better orbital overlap and polarize bond formation. So in this case, H2S. Larger orbital, that means faster reactivity. Sorry, my pencil is getting very slow, so I think we'd end this soon. Larger orbital and less electronegative atom. Okay, so that's the criteria for that one. All right. Let me just clean up here. Faster reactivity. All right. Wow, it's getting late here. I was supposed to be at work. Okay. All right. So NH3 versus NH2 minus. So remember, the more negative charge you have, the better. So NH2 is fast. It will be resulting in faster SN2 reaction. So we'll obviously have cyclohexylbromide versus the fluoride variant. All right, so remember the more electronegative you are, the better the leaving group. Well, sorry, no, that's false. The larger the atom, the better leaving group you'll be. So your leaving group's dependent on the strength of the conjugate acid. So HBr, right? We compare HBr to HF. So HBr is greater than HF, right? In acidity, so Br should be the better leaving group. So HBr, better acid, weaker base. So it'll be a more stable base, easier to depart, and so you get a faster reaction. So it's also based on like thermodynamic stability and what makes a better acid. Okay, so better acid, better leaving group, stronger conjugate acid equal better leaving group. There we go. All right. H2O versus NH3. All right. So in this one, we say the less electronegative atom wins. So in this case, it's more about electronegative atom. But in this one up here with sulfur, it was more about the size. So here, NH3, less electronegative. So you're less electronegative, you're more easy. You're easier to share electrons, right? So that's why. Okay. All right. How about we do F minus? Oh shoot! Did that just glitch? Versus I minus a product solvent. So remember, F minus. So when you're an A product solvent, remember the more charge density you have around an atom, the more reactive it is. So the less charge density you have around an atom, it's going to react slower. So in this case, when you're an A product solvent, fluoride won't be tied up as much with the solvent because it's not protic. So fluorine would win in this case. But if we switch to protic solvent, iodide would win, and that's because the solvent molecules would trap the fluorine better than iodine, because iodine is much larger, less electronegative, so the charge, it's mainly due to the size. Because iodide is larger, the charge is more separated and not as concentrated as on fluorine. So fluorine would experience more hydrogen bonding or interactions, dipole interactions with solvent rather than iodine. So the things will be flipped if we did protic solvent. All right. We have, damn, I can't remember the name now. I'm going mad. Edoxide. So this is edoxide, the conjugate base of ethanol versus tert butoxide. So remember, when we have a bulky nucleophile, it won't favor SN2, so we're gonna choose edoxide. So less bulky nucleophile. All right. So we talked about this one. Whoops, it's not OME. Sorry. So this is that's not a methyl group. That's methane sulfonate versus oops, I think I drew it wrong. So remember, these look identical, right? This looks primary, but what's the difference here? Remember when we start substituting at one carbon away from the leaving group? That also inhibits SN2 reactivity. So this is a bulky substrate. So bulky substrate. So bulky substrate. So we could just say bulky near carbon with leaving group. So when that happens, we get slow SN2. Okay, so that's not going to be very good. So this one is our winner here. It's primary, it's unhindered towards the center of reactivity, so that'll be faster reaction. Okay? All right, let's move on here. All right. So let's just say we have two different substrates here. All right. Sorry, that's supposed to be wedged. So if you query distinguish between wedge and dash like that, you're fine to use that. I don't care. I don't really have a preference. Okay, we have this substrate, and then we have this one. So these look pretty similar, right? And that has to do with the conformation. So you might have seen this in lecture, but you know, there's one conformation that would be better, right, than the other. Okay. Gosh, what is the difference? Is there a difference in this one? I don't know. Ah, yes, sorry. I'm just being a little slow today. Right, so remember, for SN2 occurs, you have to approach from the backside attack. And so if we try to approach from here, right, the arrow would, we try to approach from, okay, let me just draw it a little bit better. So to approach, we have to go here and attack, get close to the molecule, we attack towards the backside attack, right? But it's kind of hindered at this position, so you will experience steric hindrance. So these reactions get slower if you have an out. That's why primary is kind of slower than methyl, and that's because this methyl group will cause some steric hindrance, and you have to rotate to a different conformation. So now the methyl is out of the way. So when that happens, this one will experience a faster SN2 reaction because now you're not as hindered as you approach from the backside right there. Okay, so this one has more accessible now. But if we think about the energies, this conformation I circled is higher in energy because now the chlorine and methyl group on the adjacent carbon atom have a gauche interaction. So that's not good. But that's why these reactions are sometimes slow, and that's because they have to get into the right conformation, and that can take time if it's not energetically favorable. Okay, so we have the less sterically hindered conformation in terms of the nucleophile approaching. All right, let's do a few more here. Now, how about we have product solvent, bromide versus chloride. Product solvent. So remember when we did the fluorine example, in a product solvent, that will be the best, the smallest atom. But now we're in product solvent, the smallest atom will now be surrounded more by solvent in product conditions. So now bromine would win. Okay, so it's the opposite. And now lastly, let's try CH3Br. Did we do an example like this? Maybe. Alright, CH3Br versus, so these don't look much different, right? It's CH3, then CH2Br. But remember, like in this case, like I just shown before, we look at this example, when there's a methyl group 1 carbon away from the leaving group, you experience some steric hindrance, so you need to rotate to an alternate conformation, and when you do methyl bromide, you don't see that happening. So unsubstituted carbon atom. So we have all hydrogens and just the leaving group, faster rate. Equal less steric hindrance. All right, so that's all we kind of need to do about SN2 and the rates of reaction. Hopefully that was a good overview. Now let's move on to the last part of our discussion here, which is, wow, this video is going to be long. I hope everyone has time to watch it. But it'll be a good thing to do. Okay, so now let's determine if we have enantiomers. Yeah, I think my iPad is getting overclocked here. So I actually upgrade, so hopefully this will be better on this last legs here. All right, so diastereomers. So is it enantiomers, diastereomers, meso compounds? So are they the same meso compound? Or do we have identical molecules? Or are they constitutional isomers? Constitutional isomers. Okay, what are they? So we kind of saw this on the practice exam, right? You might have saw this. All right. So, all right. So right off the bat, if we look at these compounds, right? So some of these you don't even need to assign R and S right away. Just look at these molecules. So first we can rule out constitutional isomers. And so they may look like they're identical, right? But if we try to superimpose them, we see that the OH and Br groups won't match up because they'll have opposite wedge and dash bonds. But if we drew a mirror point here, it looks exactly like the other molecule, just reflected back, right? So these are enantiomers. So we call those enantiomers. All right, so that's exactly a mirror image, and they're not superimposable because if you try to put one on the other, it's like putting your hand onto your right hand. They won't match up. Okay. All right, so that's that one. All right, let's try a Fischer projection. You can also assign R and S. That's totally fine too, but sometimes that's not necessary in the interest of time here because you only get 50 minutes. Okay, so we get Cl, and then I believe another H here. Okay, so now let's draw the other molecule, Cl. H. CH3, OH. Okay, H. All right, so they look like they have the same connectivity, so we can rule out constitutional isomers. Now, let's think about what's going on here. Okay, so I think the easiest thing to do, if you don't want to rotate things, the easiest thing to do is assign each of the stereocenters RS. let's go with the first one. 1, 2, 3, 4. All right. So hydrogen is on, remember, the horizontal is the wedge, so it looks like it's 1, 2, 3. It looks like it's S, but hydrogen's on the right position, so it's R. So let's label this R. All right, let's do the second stereocenter now. Chlorine is going to be number 1. Hydrogen's 4 again. And then 3 is going to be the rest of the chain here, and then, sorry, that's 2. I meant 2, not 3. 3 is the methyl group. Okay. So hydrogen at this time, hydrogen is on the dashed, because remember the vertical is the dash. So we go 1, 2, 3, we get another R. All right, so that's R. All right, so let's do the second molecule here. So 1, 2, 3. Okay, it looks like it's S. If we go 1, 2, 3, and then 4 for hydrogen, but hydrogen is on the wedge, so it's reversed. So it's actually going to be R here. And then let's look at the other stereocenter for this molecule. We have hydrogen's 4, OH is 1, and then the alkyl group is 2, ethyl group is 3. And we see here that if we go, hydrogen is now on the dash, so we could just assign it regularly, and that'll be our assignment. 1, 2, 3. It looks like it's R. So you see here, both centers are R, and both molecules, they look the same. So this is going to be identical molecules. So no matter how they're drawn, right? They're identical if the stereocenters do not change here, and that's what we have. All right, so that's how you do that one. Okay. Let's go on here. All right. Cl. Then we have okay, we don't really need to draw this like this, but man, this lagging is really starting to irk me. But it's been running probably now close to over 2 hours, so you can see why it might be slow. Okay, so then we have H, Br, CH3. Okay, so let's say we have a chlorine here, an H here, and then CH2, CH3. So sometimes we will write things in different ways just to confuse you, but that's your job to debunk it. Okay, so we compare both of these structures. There's a chlorine atom attached to a carbon with a methyl in one group, and then in the other group, it's attached to a methyl and a bromine. So the bromine and chlorines are switched on the carbon atoms. So these are not stereoisomers. These are constitutional isomers or structural isomers. So we'll say constitutional isomers. You can also say structural isomers. That's the same thing. All right, last one. All right, if we look at these two cyclohexanes, they're both 1,3, right? 1, 2, 3. And 1, 2, 3. But one's cis and one's trans, right? So remember the relationship between cis and trans? They're not mirror images, and they're not superimposable, right? Because if we look at these stereocenters here, all right, let's call this alpha and beta. So alpha stays the same, right? So letter A is the same, but letter B has switched configurations. So when you switch a dashed to wedged or wedged to dashed or vice versa, that changes the stereochemistry from R to S or S to R. So when we have only one stereocenter changing and the other is the same, that's called diastereomer. All right, so that's it for determining the relationship between stereoisomers. Hopefully that was helpful. Now let's go on to at least one mechanism question, just to give you an idea of what's expected. So for the mechanism, I'm going to show you how we will do these mechanisms. Say we have tert-butyl bromide. Okay? And you're going to react it with methanol. Okay. So what we expect is you draw all the arrows and then draw the electron pushing arrows just like we saw in the first exam. Okay. So this is, well, what kind of reaction is this? Well, it's a tertiary halide, and we have a weak nucleophile that's also weak nucleophile. So a poor nucleophile. So that screams SN1. So we're going to say SN1. But we should also say E1 too. Okay, so we're going to show the pathways for both. So let's draw this out separately here so it's very clear. Okay. So the bromine would leave. So remember SN1, it only depends on the electrophile. So this will leave. So I don't know how she showed it in the lecture, but just if you don't write the double-headed arrows, usually we don't get points for that, so it's okay. But so it's okay for now, but you should think of these as equilibrium processes because it can go backwards. Because the bromine could leave, but then it could just reattach because it's a good nucleophile. So you should draw them going back and forth. So now we have a planar intermediate, or carbocation intermediate, okay? So now we can also go in the forward direction because it's going to go forward or backwards. We have now our nucleophile here, but we also have bromine. So eventually it will go, it's an equilibrium process, so eventually it'll go forward. And that's where you kind of trap it. So we're going to show it bonding to the positive charge here, and now you're going to form your other intermediate, the oxonium ion. So don't forget your formal charges here, like that, and then it bonds to the H3C, like that. Okay. Alright, so this is an acid-base reaction now because now the bromide will come in even though it's not a very good base. It's okay because this oxonium ion we have drawn is very acidic, so the hydrogen just wants to be removed by anything within its vicinity. So we need to show two arrows here because the electrons from bromine are going to grab the hydrogen. So those shared electrons, the hydrogen was sharing with the oxygen, must be displaced, and it goes right back to the oxygen. So now you form a neutral ether compound, like so. So in this case, there is no stereo really because it's not chiral. Well, you could draw you could draw one if you like, but you don't have to. So OCH3, So just for clarity, let's just make this bond. Let's just show it as a like. Let's just keep it like that. Let's bold it a little bit, just to show that you can attack the carbocation from the top face or the bottom face. All right. So let's balance our reactions. So we're going to write HBr here. So that's one of our products, the SN1 product. SN1 product. Okay. Now we need to look at the second product. So we also have this occurring. The carbocation now will also be involved in it, unfortunately. So your carbocation can also be quenched or consumed by reaction E1 process. So E1 can come here, get the proton, and then this proton will lose its electrons to form a double bond with the alkene. And so that's a process that can go backwards. So let's write it as 2 arrows here. And then we can draw the final product as this alkene here. And there's only one product because all the methyl groups are equivalent. And so we get this as our E1 product. Okay. There we go. So sorry about that little hiccup there. Now let's move on here. All right. So the last thing we want to do is talk about IR spectroscopy. Okay, so I'll do one example. Okay, so we're going to just predict what these compounds could be. Okay, so here's my IR. I'm going to draw a very generic IR. So here's my IR. So here is 4,000. Here is 3,000. Let's make this peak a little bit more appropriate here. So let's just make this a single line, make this a bigger peak, so it's kind of appearing at 3,100. Okay. And then this is going to appear at, let's make it a little bit sharper, at above 28. And then right here is 2,000. So this appears at about 17, 16, and then this peak right here is 1,000. So not very drawn the scale here. And here's 500. Oops, not 5,000. So let's just see these peaks here. So this peak here, this looks like an OH peak because it's between 3,000 and 4,000 and it's very broad. So that's using alcohol. This peak right here, so let's draw it a little more clear here. Actually, this is really bad. Let me just redraw it. But I'm afraid if I redraw it, it'll erase. So maybe I just have to outline it. Okay, there we go. So that one looks like it's a little bit past 3,000. So remember, that's usually when it's a little bit past 3,000, near 3,100. That's usually sp2 carbon. So this is usually the sp2 CH bond. So it'll correspond to this bond right here. So it's usually the CH bond, right? So we're going to say this is sp2 CH, like that. Okay, so that's what we would expect. All right, this large peak at around 3,000 here. This is usually sp3 CH, so alkane. All right, this peak that appears a little bit before 3,000 is usually the aldehyde CH. So it's usually the aldehyde CH bond right there. Okay, so maybe we could just point it directly to this carbon. Okay, oops. Losing everything today. Okay, there we go. So that will be that peak, and then this sharper peak here, that is our C double bond O peak at 1700, and then roughly right next to it, a little bit further down, that's our CC double bond peak right there. Okay, so now that we have all those peaks there, let's say we can have a number of structures. CO, so we will provide spectra that is definitely interpretable and has clear peaks indicated, so you don't have to worry about seeing peaks that aren't necessarily or spectra that's not that has pretty good or all right quality. Alrighty. Alright. So we'll give you a number of structures to choose from, and you just have to suggest which ones are possible. And if there's a tiebreaker, you probably have to choose more than one, but usually we'll make it like so that it's only one or the other. Okay. So I drew a bunch of carbonyls. They look like all aldehydes. Okay. Alright, so there's a lot of structures here. Too bad I can't fit it on one page. So I'll have to go back and refer back to it. Hopefully my iPad doesn't die by then. I know I'm asking a lot from it. So my recommendation, if you see these structures, you cross out the ones that clearly don't match the spectra completely, and that will help you limit your possibilities here and do, you're like kind of limiting some of the options, so it's easier to narrow things down. So the thing about IR, it doesn't really necessarily tell you the locations of these bonds. It just tells you what's present in the molecule. So when doing these IR problems, you should keep that in mind. What actually tells you the connections is NMR, but that won't be tested on this upcoming exam. All right, and here's the last row. Okay, so there's a lot of molecules. So now we have some ketones. So is it a ketone or an aldehyde? And lastly, we have additional ketone here. Okay, so there's all our molecules. So let's just summarize what we have. We have an OH, an alkene, CH bond, an alkene double bond, a C double bond O, and an aldehyde CH bond. So we can eliminate all the ketones because we know we don't have a ketone. It's an aldehyde, so let's eliminate the last row. All right, so we know we have an OH group. So we can eliminate the ones that don't have OH groups. So we can eliminate the first row too. Now let's see what we have. OH, so everything here has an OH, good. All right, so does every one of them have a double bond? CC double bond? No. So we can eliminate this one and then this one. So now our options are these two molecules here. So we have a CC double bond, good. OH bond, good. And then an aldehyde and a C double bond O aldehyde. So aldehyde, aldehyde. So both these molecules match our IR spectrum, so it can be either one of these isomers. So we can't know for sure what isomer it is unless we do further spectroscopy experiments. Okay, so that's how you would decipher an IR. I would always, label the peaks first, so it helps with your assignment. That's a smarter way to do it. And then use process of elimination to figure out your molecule. Okay, so that's it for this review. It's very long, so please get some time to go over it and, review your notes, go over more problems for more practice, and good luck on the exam. So that'll be it, everyone. And if there's any other questions, feel free to contact me. All right, take care. Hello, everyone. I'm back. I forgot one more topic: synthesis. So let me go into that right now. We'll do a few synthesis problems. So there's not many different reactions we have learned so far. So there's not much, we can actually do yet. So let's just do a few. All right, I have this molecule. Okay, to make it simpler, let's just say, okay, CH2 CH3. And say I want to make this molecule. All right, so I want to make this alkene here. Okay. All right, so you may recall that to make an alkene from an alkyl halide, you want to use a bulky base. So in this case, let's just redraw this out here. CH2, so we're going to use CH2, then there's a bromine here. Let's just make it an no stereochemistry involved. And then we have a CH3 here. Okay. So then we want to go to this molecule, which is basically, we just replace the CH2 with an alkene. So remember, here we will need a bulky base. Bulky, strong base. So what will go in this box here? So let's just say there's a box here. We'll just put a magical box here and say, okay, to make this molecule, we need a bulky base. So the bulky base we know are, there's LDA, which is this group here. Lithium diisopropyl amide. So that's a strong base. We can use sodium, sodium tert butoxide or potassium tert butoxide. So those are some common ones too. So if you use either of these three, they should work. So I would choose something like sodium OCCH3. Because to make this connection, you need this group to leave. So you need this group to leave, and the only ways we know to form from alkene, haloalkane to alkene is a strong bulky base. So we will use something like this, okay? Like that. So that's how you figure that one. All right, let's do a more complicated example now. Say we want okay, so say we start with this methyl cyclopentane, and we want this group here. What's a good example here? Okay, say we start with it. We want this, and we want to put a cyano group on here. How will we do that? Okay, so the thing we need to think about is we're replacing this H bond with a cyano bond. So we're breaking that bond, right? So we need to figure out a way to, first we need to get into this position. We need to figure out a way to make this a good leaving group, right? So this would be a good leaving group. And then we can use SN2 chemistry to do nucleophilic substitution. Or well, not SN2. In this case, it'll probably be SN1. SN1 type chemistry. Okay. All right. So what's one thing we can do? So how do we functionalize a alkane? Well, there's only one reaction we know: radical halogenation. So radical halogenation. Okay. So one example, we can use X2, right? And then light/heat. So that's something we want to do. But what should X2 be? Well, we need it on a tertiary position. So fluorine won't work because it's not selective. Chlorine won't work either because there's some way more CH2 positions, secondary hydrogens, than tertiary or primary. So chlorine won't work. So chlorine will go to secondary position. Fluorine will give you all kinds of positions. In this case, it'll probably give you secondary too. So primary, secondary, tertiary. So our only option is bromine because it'll provide the position we want in the greatest yield because the selectivity for bromine is very high. So we're going to say Br2 and then, like heat or light. Doesn't matter. All right, so then we erase this X. It'll give us the bromine we want. And then we can do SN1 chemistry, and then it'll give us the desired product. Okay, so in this case, we can do... so since cyanide is really not... so cyanide should give you the major product as the substitution product. So we can do sodium cyanide and then maybe a, in this case... appropriate solvent here would probably be, a DMSO. So any polar aprotic solvent. So since we want to favor substitution and not elimination, we want to make sure we use a polar aprotic solvent so it favors SN2 or SN1. Okay, so in this case, you would think, oh, we want to why not protic because it's SN1? Well, the reason for that is that our nucleophile is charged, so it's negatively charged here. So negative cyanide and positive sodium. The sodium will just be in solution. So to limit the reactivity here, we want to make sure we get a polar aprotic solvent. So the reaction goes to completion and favors substitution instead of elimination. So we might get some E1 product, but here we want to make sure we get mostly substitution. So we should use a polar aprotic solvent. So when you have anything charged, like a good nucleophile, you want to use a aprotic solvent and make sure you don't get elimination as your byproduct. Okay? So that's pretty much all we can ask you. We can also ask you something like this. let's see here. Say we have good leaving group, mesylate. And then we want to get a situation where we get this group here. Okay, so the key differences here. Look at the stereochemistry. It's you have the same stereochemistry, so same stereochemistry as reactant. So how do you get the same stereochemistry through a substitution reaction without getting the other isomer, right? So what you have to do is you actually have to think about the mechanism. So you can't do SN1, right? Because you lose 50% of your product to the wrong isomer. So SN1, not good. So we're not going to do SN1. We're going to actually do a few SN2 reactions. So first we need to convert it to another good leaving group. And so what we can do here is do something like sodium, iodide, and then a polar a product solvent like acetone. Like something like that, and then you can separate, I believe, these reactions. But I don't know if acetone is the best solvent, but it's okay, just any polar a product solvent. So now when we do this, this will be an SN2, and then we'll invert the stereochemistry here. So now we have the first reaction done, but we want to invert it again to get the ideal product. So we're going to do another SN2 reaction. So we're going to do something like sodium formate. All right, so how do we determine? So sorry, I'm drawing a blank here. Sodium formate. So we can just draw it. So you're going to take the conjugate base of formate, which is this group on this group that I've drawn in the product, but with like this. Okay, so it's negative charge. So you can draw it like that, negative charge, sodium plus. You can buy it as a salt, so it will work. And then we can just use another polar solvent like DMF. And then you get your ester there. So that will be another way to make this product. Okay, so when we do this, we do another SN2. It will revert stereochemistry back. And so then you go from wedge to dash, and then dash to wedge. So you have to do two subsequent SN2 reactions. So that's one way to do to get the right stereochemistry. Now there are more sophisticated methods where you don't have to do this, but that's an advanced reaction, and we won't go over that. So, but this is using what you know. This is what you would do: two subsequent SN2 reactions. You don't want to do SN1 because if you do SN1, you lose 50% of the stereoisomer you want. So if you do it twice, it's not going to be productive. So in these reactions, you want to make sure you get the most yield out of each step. Okay? All right, let's just do one last one just to change it up a bit. Okay. Well, which one should we do? Good question. Well, I already showed you elimination. You know, this might just be good enough. So, out of all the problems that you could see, I pretty much gone over all three. 1, 2, 3. So, I think I will stop there. Okay, I think that sounds good. So, but should we do another one? No, I think that covers all of our bases. So yeah, I think that's pretty good. Yeah, so I think that's pretty good. So sorry about that. That'll be it. So I don't want to overload, do too many of them. So, but there's no more. There'll probably be at least one synthesis problem. So I would study your reactions to make sure you have all the reactions down, and that you can plan out a synthesis and get the target molecule. And the key to doing synthesis is find out what kind of bonds you want. So in this case, we want to break this bond and replace it with O, this formate group. But in order to do that, we have to first, we can't just do it directly, right? Because we need to maintain the stereochemistry. So that's why we put that reaction second, so we can invert the stereochemistry back to the original stereochemistry that we started with. And so we can get the right product. So my suggestion is find which bonds you're breaking and find out how you can make that connection with the chemical reactions you know. So it's not always clear to see what reaction you need to use. So you need to know your reactions very well and be able to say, okay, I need to break this bond, so how do I do it? And then I need to replace it with this bond, so what's the reagents do I need? So I would practice doing chemical reactions and then applying them in synthesis, because that's the main goal in organic, is to apply your reaction knowledge to designing new compounds and solving problems of importance using these reactions we know, and how can we use it artistically to make compounds that we seek after. Okay, so that'll be it for the review. Sorry, I sure included this in my other video, but that'll be it. So this is synthesis. If there's any questions, please come see me. All right. Good luck, everyone.